Buenas tardes, agradecemos su presencia a esta conferencia número 8 del ciclo Panorama actual de las ciencias atmosféricas, y esta vez tenemos el honor de recibir al doctor Patrick Arnott del programa de ciencias atmosféricas de la Universidad del Departamento de Física de la Universidad de Nevada en Reno. El doctor Arnott obtuvo su grado de licenciatura de la Universidad de Southern Colorado en Pueblo, no Puebla, Pueblo. Y realizó una estancia de verano en el Centro de Investigación de Xerox en Palo Alto, y después obtuvo sus grados de maestría y doctorado en la Universidad Estatal de Washington, con el tema de aspectos geométricos de la propagación y dispersión de ondas. Después realizó postdoctorado en el Centro Nacional para la Acústica Física de la Universidad de Mississippi. Posteriormente empezó a trabajar en el Desert Research Institute, trabajando en el muestreo in situ de nubes cirrus. Me corrigen si me equivoco, ya saben que no soy experto. Aspectos geométricos de la transferencia de radiación infrarroja y desarrollo de instrumentos fotoacústicos para las mediciones ópticas de aerosoles. Como resultado de su trabajo ha obtenido 2 patentes y la transferencia de 2 instrumentos para la fabricación industrial. Y desde el año 2005 trabaja en el Departamento de Física de la Universidad de Nevada en Reno. Es el director del programa de licenciatura en ciencias atmosféricas y es investigador en la espectroscopía fotoacústica de aerosoles. Es conveniente mencionar también que fue ganador del premio Benjamin Lee, sí, por sus sus contribuciones sobresalientes en las técnicas e instrumentación para el análisis de aerosoles en el año 2013. Y esta vez el tema de su presentación es Aerosol Light Absorption and Scattering.
Gracias. Puebla es hermana ciudad de pueblo. Gracias por la invitación aquí. Unfortunately, I'll have to give the talk in English. Next time in Spanish, hopefully. Okay, so the talk today is going to consider, among other things, these photoacoustic instruments, and what I'm going to say applies to all of them, including sort of our first one, the PASS 1, PASS 2, PAX, and PASS UNEM. I wanted to start off a little bit by discussing our atmospheric science programs in Reno. We have a grad program that's been in existence since 1965. Our undergrad program since 2005. We have about 20 faculty members from the Desert Research Institute that participate, and about 4 faculty members full-time on campus that participate. Here are our students of physics and atmospheric science participating in a senior thesis presentation by one of the students as well. I'll give you kind of an idea of what our students look like. Okay, so as an outline of what I want to cover today, I'll talk some about the aerosol optics and microphysics, the optical coefficients of an air parcel, and it's very simple in some ways. That's the absorption coefficient, which is the death of photons. Light energy goes to heat. The scattering coefficient, it's sort of a second life for photons, redirection, and then the extinction coefficient, which is the sum of both of those. And I'll talk about how we measure that and applications of the coefficients and science insights. So aerosol optics in a broad sense is coming about as a consequence of societal activity, nature in action, photochemical transformation, and meteorology. It seems that everything that we do in society has a climate impact of some nature or other. Our decisions about how we transport, what we eat, how we treat our land surfaces, where we live, and the sorts of things we make have climate impacts, and a lot of those climate impacts are expressed through interactions with atmospheric aerosol. So the starting point for the optics is really quite simple. We have a particle in the atmosphere that's suspended, and we have light impinging upon it. And we have a process of absorption where some of the light goes into heat, and we describe that with the absorption cross-section. And we have some of the light that goes into scattering through processes of reflection, diffraction, refraction, and tunneling, and those processes are described by the scattering cross-section. So when we look at a collection of particles like we have here, we're interested in seeing what happens to this beam of light when it transfers through these particles and comes out on the other end. So in order to deal with a collection of particles, we might use something for the direct beam of light in the absence of multiple scattering. Use the Beer's law, where we have an optical depth here formed by the extinction coefficient and the physical path length here. And then we obtain those coefficients by integrating over the size distribution of the aerosol in our sample. And we integrate that with our cross-sections to obtain these coefficients. So the dimensions of the coefficients are inverse distance, 1 over distance. And the key thing that makes aerosol complex is that these cross-sections depend on aerosol size, shape, and composition, and of course on the wavelength as well. So this is a depiction of the cross-sections per unit mass for individual particle. And the type of particle I'm considering is a spherical particle made of soot. And we're going to consider a wavelength of 550 nanometers, sort of green light. And in order to make this calculation, we need to ascribe a density. That density for soot is about 1.2 grams per cubic centimeter. The real part of the refractive index, which is largely associated with scattering, is about 1.75, and the imaginary part is quite large for soot. That's what's associated with absorption, and so that's typical for a value for soot. What we see on this axis, we have the particle diameter, and this axis we have the cross-section per particle mass. We see that when we start with very small size, then the absorption per unit mass is independent of diameter for some range. And that means that we can use the absorption coefficient to also learn about the mass concentration of the black carbon or the light-absorbing particle in the atmosphere, because the cross-section per unit mass is basically flat. When we look at the scattering cross-section for small size, because the diameter of the particle is much smaller than the wavelength, we have very little scattering at small size. And when we get into larger size, we have a resonance region where the absorption cross-section and scattering cross-section have their peaks, and that's in the vicinity of where the diameter is roughly close to the wavelength of the radiation, about a factor of 2 smaller actually. And then when we go to very large size, we have a 1/r dependence because the cross sections just depend on the geometrical area of the particle in that circumstance. So then when we divide by particle mass, it makes it a 1/r dependence there. The scattering, by comparison to absorption, does not ever have a very flat region like this. So in general, we can't really use a scattering measurement uniquely for determining the mass concentration for particles. Okay, so when we look at radiative forcing by aerosol in the atmosphere, this is an example of a very sort of simplified linearized model meant to represent global behavior, just for helping us understand how aerosol contributes to climate. What we have on this axis is the aerosol optical depth, a measure of the total aerosol content in the entire atmosphere, and the radiative forcing on this axis in watts per square meter. So when we look at typical values of aerosol optical depth, roughly 0.2, 0.3, then we can see that for strongly scattering aerosol, there's a cooling effect that is exhibited by the negative value for the forcing, meaning that there's less radiation being absorbed in the system in that circumstance. Yet when we have strongly absorbing aerosol, the sign can change, where we have a warming effect in climate by the aerosol as well. So the cross-sections and the coefficients are important for helping us learn about the aerosol radiative forcing in the atmosphere. So now I want to talk about some of the microphysical properties of black carbon aerosol specifically. So this is a TEM image from Arizona State University, and it shows what might be typical for a particle freshly emitted from a diesel vehicle. So those particles are formed by chain aggregate monomers that are coupled together to form an overall particle that's rather large, very large maximum dimension compared to the monomer size, but there's not much mass in that location. So that means that this particle can transport over long distances, even though it's a large particle. And when we look at the monomers, they tend to have 10 to 50 nanometer diameter. The simplest way of calculating the absorption cross-section for a composite collection of monomers like this is just to use something like the Lie theory for an individual monomer and then sum them up, just a simple sum for the total cross-section, and that gets you pretty close to the right answer, it appears. When we look in detail at the monomers, they tend to have a bit of an onion shell-like structure, perhaps, as well. So we see these chain aggregate fractal sort of black carbon particles, not only coming from diesel engines, but also from burning of different kinds of plants in the atmosphere. This is chamise smoke, dry chamise smoke that we sampled during a campaign in Missoula, Montana. And the chamise smoke, if we didn't have any other idea, we might think that it's sort of like a diesel soot particle as well. It behaves very much like that. The chamise bush is something like a flowering sort of shrub. And flowering shrubs tend to have this sort of behavior as well. They have quite a lot of absorption as a particle compared to the burning of other types of fuels, which I'll mention some later too. Now, the interesting thing about burning is from smoke, smoke from plants, is that you often have maybe a little bit more complicated chemistry. You often have some inorganic material that also is on this particle, and that can facilitate uptake of water when it's humidified. So when this goes into the atmosphere, if it has some black carbon in it, as well as some inorganic salts, then it can become humidified, and as a consequence of that humidification, then often what happens is that overall large maximum dimension now collapses into a much smaller size as a consequence of the interaction with the water vapor. It can also happen with certain types of organics that will condense on the black carbon particles in the urban environment. So what's happened now is that before, the monomers were all available for absorbing light. And now, depending on the wavelength, some of the monomers on the inside of this particle may no longer be available for absorption. So we've changed the microphysics of the particle by processing in the atmosphere, resulting in a change of the optical properties. When we saw this in our campaign, we were very excited about it, of course, and we wanted to understand it. Because it's such an interesting phenomenon, we figured that somebody else had observed it in the past, and we tried to find the first paper ever written on collapsing black carbon soot particles. So we looked in the literature until we found this paper here. And this one is a little bit bizarre. There's a volunteer here, and there's an engine. And this volunteer is breathing in exhaust from this engine in order to find out how long it takes for lead to be processed in his body after he is exposed to it and days thereafter. So it's sort of a crazy thing. It must be a very dedicated researcher. But yet I also think that many times when we walk around on the street, we're doing exactly the same thing one way or another. But what happened during this campaign was that they also did some photomicrographs of the particles that were breathed in by this fellow. And so then these were the particles before inhalation, and some of the particles came out of his lungs as well, and they had the same collapsed shape that we saw in our smoke as well. So this might be very well happening with all of us every day. Key thing, though, from an optical climate sort of processing perspective is that the optics of the particle are quite different when they're stretched out like this as compared to when they are much more compact like this. Okay, so I want to talk, let's see, about the parameters we use for radiative transfer for aerosol, and these are all. This is a dimensionless parameter known as the single scattering albedo. It's a measure of the fraction of the extinction that's due to scattering. So the number is between 0 and 1. And when we have completely scattering aerosol like sulfate, the single scattering albedo is very close to 1. Especially for the optical or the sunlight wavelengths that are important. Then when we look at something like diesel soot or the chamise smoke, the fresh chamise smoke, then the single scattering albedo is much lower. It's about 0.3. And this value depends on chemical composition, particle size, morphology, and wavelength. We also use the parameterization of the wavelength dependence of the light absorption. as well. So we use a coefficient here to represent the wavelength dependence. Wavelength is lambda. Alpha is the angstrom exponent for absorption. And practically in our lab, we use 405 nanometers and 870 to determine alpha. Alpha is about equal to 1 for motor vehicle emission generated black carbon for the sort of diesel soot or chimney smoke. And the biomass burning aerosol can have alpha using these wavelengths as large as 3.5. And that's because at the 405 nanometer wavelength, some of the organic aerosol also absorbs strongly, and we call that brown carbon aerosol. In addition, dust, like Thomas Gill was mentioning and we heard about for Beijing yesterday, dust has an angstrom exponent for absorption that also can be quite large because it absorbs preferentially in the UV and near UV wavelength range as well. Similarly, for the scattering coefficient, we use a parameterization, B being the angstrom exponent for scattering in this case, and we use any available wavelength for determining B. Actually, B tends to be wavelength dependent itself. So we find that, roughly speaking, if you want to sort of have a rule of thumb, the B value for a city might be about 1.6, but it's going to depend on particle size pretty strongly. For Rayleigh scattering by gases or very small particles compared to the wavelength, B is 4, and for the coarse mode dust, B is going to be less than 1. It might even be 0 for large dust by comparison. So this is a mnemonic that I like to use to help remember the behavior of B. If we consider very small particles, B is large. If we consider very large particles, then B is small. So, can be used as a mnemonic to help remember that behavior. Shifting gears now, I want to look at how we measure aerosol light absorption, how we obtain it. So we can obtain it from calculation, from in situ measurements, either filter-based or photoacoustic primarily, and we can also obtain it from remote sensing. I'll concentrate on the in situ measurements. First, I want to talk about the filter-based measurements and the challenges associated with them. So with the filter-based measurement, we shine light through a filter where we have particles embedded on the filter. And it's a very simple measurement to do, but there basically is a main problem associated with trying to learn about what that particle might do in the atmosphere versus what it did on the filter. So that's the challenge. So we find that there's a bit of interference between absorption by particles and scattering by particles in the filter media. And we can correct for that by using a radiative transfer approach. It's not a huge effect, but for completeness, it's worth looking at. And the other thing that's different between filter and photoacoustic methods is that there's a limited dynamic range. If you're in a place that's very dirty, then the filter is going to fill up with aerosol pretty quickly and have to change position. So that's going to maybe limit the data stream. As I mentioned, it's a very simple measurement. We have light. We have a sample air being pulled in from the atmosphere through a sampling chamber and deposited on the filter by use of a pump here. We shine light through that filter to a photodetector, and as the light absorbing particles build up on this filter, we have less light coming through. There is a bit of an influence of scattering aerosol as well that backscatters some of the light, a small fraction. And then there's also an effect that if you start off with a clean filter and you have particles lining up on it, then it's going to have a sort of a layering effect on the particle absorption measurement. This is probably the simplest measurement that's used for light absorption measurement, and it works quite well. It's the PSAP, and two different instruments have been developed. One is at a single wavelength, and one at 3 wavelengths at the same time. It has a filter cassette that is changed manually when the transmission through the filter drops to an appropriate level. And this is the filter cassette showing the reference filter and the exposed filter here. there's one major advantage of filter measurements over photoacoustic measurements. That is that because the particles are piling up on the filter, then the noise, because you have many chances to measure them basically, the noise is going to decrease as 1 over the measurement time. Whereas in the photoacoustic instrument, because you have one shot at doing the measurement when the particle goes through, it scales as 1 over the square root of measurement time. So that's one very useful thing when you're trying to measure in very clean areas with a filter-based sampler. You can take advantage of that. Let's see. The other type of filter-based instrument for light absorption that's very common is the aethalometer, and it automatically makes filter changes when the transmission drops to an appropriate level, so you don't have to have a person worrying over it so much as with PSAP. The AE31 works at 7 wavelengths from the UV to the near IR, and the UV, just as in the photoacoustic instruments, is useful for brown carbon determination, and the black carbon determination can be done essentially at all wavelengths. Whoops. This is a cross-section of the aethalometer filter to show how the particles embed in the surface of the filter. This is a pristine filter, so we take the filter and cut it and then look at it under a microscope. And it's a very white, very strongly multiply scattering environment for the particles. So when we have a particle that lands, say, right in here, then there's going to be a direct beam of light that goes through, but a lot of chances for multiply scattered light to cause absorption as well. So you get an enhancement of the signal essentially by having a multiple scattering environment where the particles are at. When we expose a filter to kerosene soot, then this is sort of what it looks like for the quartz or glass fiber filter. The particles embed roughly in the first fourth or third of the filter, and what we're hoping is that they sort of disperse as much as possible so as not to cause sort of a shadowing effect as the particles build up. By comparison, when we look at Teflon filter, Teflon is much less penetrable than a quartz or glass fiber filter. Then what we see on the surface is that, looking at the size here, these look like 20 micron diameter black carbon particles. Well, we just don't see that in the atmosphere. So this is an event that we measured in Reno, typical sort of morning rush hour, and we had a Teflon filter in a sampler making analysis, and I think what's going on with this is that there's a preference for the particles to coagulate rather than to make a nice uniform layer on the Teflon surface. I think that they tend to coagulate to form larger particles, and then that makes the interior of this large particle now no longer available for absorption either. So the interpretation for measurements that are done on a Teflon filter can be pretty tricky. This is a similar example for Teflon, where we exposed it to kerosene soot for a test, and you can see that the soot also tends to pile up on the top surface of the Teflon. Okay, next I want to consider the photoacoustic instruments, and I'll go through the basic idea. It is based on and calibrated with first principles, time resolution of about a second. It has a very large dynamic range because we use a microphone as a detector. And a microphone, to be useful for human applications, we have to have a large dynamic range because our hearing tends to be sort of logarithmic. And so we must be able to work with a microphone, whisper, tiny, tiny little whisper, to the roar of a jet, which I won't try to imitate. And so then, as a consequence, it makes a good detector. The instrument has a reasonable sensitivity that can be increased by using a more powerful laser, and we've got it to the point of being able to rack mount it, and we've used it even on aircraft operations as well, flying around with it. It's not simple to use on an aircraft, but it's possible. This is a schematic of the instrument. We have light coming in from a laser on this side, and it's either chopped with a mechanical chopper like this, so the light goes through the holes, or we use electronic modulation. And we we modulate the laser power at the resonance frequency of this acoustical resonator. We have air being pulled through the system by the pump, and we have a microphone on the wall here. We have a photo detector to measure the total laser power that's being used. So when the particles absorb light, they heat up, and the heat transfers very rapidly to the surrounding air, rapidly compared to the acoustic frequency that we're using. So the air receives the heat, and what does air do when it receives heat? It expands, and then the light's off, and then it's on. So we get a sound that's created through the process of light absorption by the particles to make a signal that depends on absorption and not scattering in that case. This is a schematic of our Pass 1 instrument, and the way that we realized it in practice was to put the microphone here, and we have one acoustic wavelength extending from here to here. So it's like an organ pipe or like a standing wave on a string. You have a pressure antinode here, a high pressure, a pressure node here, low pressure, pressure antinode in this region here where the pumping of the sound occurs to create the photoacoustic effect. And then we have the pressure node here, low pressure, and pressure antinode. And at this end, we put a sound source, a piezoelectric transducer, to occasionally do the acoustic calibration of the system as well, to find out what the resonance frequency is and the quality factor. Both are needed for the measurement. We are pulling the air through the system this way, and because we have antinodes at these two spots, nodes at these two spots, it's much like standing waves on a string, where you have a node on a standing wave on a string. You can put your finger there, and it doesn't affect it. It still stands. So in the acoustical resonator at a node, we can put holes and use that to get the light through and also to get the sample air through the system as well. Then, in order to measure the scattering cross-section, we put in a detector right here where we get an integrated scattering measurement. Forward scattering comes from here, 90 degree here, and back scattering from this direction here. So by this means, we're able to measure the important cross-sections for the particle. We can measure absorption, scattering, and extinction. We get extinction two ways. First, we can just sum absorption plus scattering. The second way is that we have a path from here to here. It's not a very long path, and if we have enough aerosol in the cell, we can make a measurement of the reduction of laser power and then use that to calculate extinction as well. And that's a very fundamental and very simple measurement. In fact, that's how we do the calibration for the instrument. We use first ammonium sulfate or a lightly absorbing aerosol, and we measure extinction in that case, and we compare it with scattering because there's no absorption. So we can calibrate the scattering that way. Then we put in kerosene soot or something that's strongly absorbing, and we measure again extinction, which is now the sum of absorption and scattering. Scattering is calibrated, so we can calculate absorption and calibrate it as well. This is a photograph of the first instrument that we made. We made it at 1047 nanometers for the University of Utah's coal reactor facility. And in this one, because 1047 is very useful for black carbon, but is not a visible wavelength, it's in the near IR, we used small cameras to look at the window so we could see how the laser beam is aligned. This is the inlet to the system here, and the outlet to the pump here. Microphone sits here, piezoelectric transducer here. Laser power is measured here. And these two units are Helmholtz resonators used to acoustically filter the sound that comes in the inlet line. So noisy low-frequency sounds that would otherwise cause problems are reflected at this point and sent back out. So we like to, when possible, acoustically filter the sound and interference rather than having to deal with it electronically. The photoacoustic instrument absorption coefficient comes directly from first principles. We have the microphone pressure, when we use a calibrated microphone, then this value is in appropriate pressure units. We have the laser power here, cross-sectional area of the resonator. Gamma is Cp over Cv, ratio of the specific heats. F naught is the resonance frequency, which we determine with the piezoelectric transducer, and Q is the quality factor. So by first principle measurements, we can get the absorption cross-section, and then we can test to see if it's reasonable by comparing with our extinction calibrations. Okay, so I want to now look at a case where we have absorption measurements in a campaign where we looked at ammonium sulfate, very lightly or non-absorbing aerosol, essentially. And we had a Reno aerosol optics experiment where we tested a bunch of instruments that are currently on the market and were coming onto the market. And so we looked at scattering by this aerosol, which was very large. It's about 525, roughly 520 inverse megameters. And we found for the photoacoustic instrument, there's no signal coming from it, as we would expect for a lightly absorbing aerosol like that. In the case of the aphelometer at 521 nanometers, we found that the offset caused by backscattering by the aerosol was about roughly about 30 inverse megameters. So there's a bit of an offset for the filter-based system that can come about from scattering. The PSAP instrument also has scattering influence that's been characterized by Tammy Bond, and the recommendation there is to say that the absorption true is going to be the absorption measured by the PSAP after scattering. 2.5% of the scattering is subtracted. So when you couple a scattering measurement at the same wavelength with the absorption measurement by the PSAP, then you can correct it for scattering, and that's sometimes important, sometimes irrelevant. Okay, now the next thing that we looked at during the Reno aerosol optics experiment was very dark aerosol, kerosene soot. And the kerosene soot, to make it kerosene lamp soot, we make it run very rich, lots of fuel, and you get this very unpleasant dark smoke from it. So during this time of measurement, the scattering values were low, because this source absorbs much more strongly than it scatters. And it was very steady as well by the measures of the nephelometer and the photoacoustic instrument. Yet the filter-based sampler has the impact, or has the behavior, that the signal starts higher and diminishes with time because of the reduction of the multiple scattering enhancement factor. Then there's a filter change, and we go back to a clean filter here, and then as we go through time further, then the signal drops again as a consequence of that multiple scattering enhancement factor dropping. So we've worked on algorithms for helping with that effect as well. So now I want to show some of the photographs, basically, of the different kinds of projects we've used the photoacoustic instrument for over the years. And many of these projects were done for developing or evaluating emission inventories and for urban air quality assessment. So this is the photoacoustic instrument in Los Angeles in a sampling van, where we have a sampler here where we take air from outside into. Photoacoustic instrument is sitting here among other instruments. So we sampled around Los Angeles. We sampled a lot of vehicles on dynamometers over the years. This is with our 1047 nanometer instrument. We looked at both gasoline-powered vehicles and diesel-powered vehicles. We even measured the emissions from aircraft. This sort of crazy measurement here, where we had this aircraft tethered on the runway, running at about 80% full power, and measured the emissions of particulate matter from it as well. We've measured in Nevada mines, Minas de Nevada, Oro Minas, and you can see it's quite dirty underground. This is underground mine, and you can see my smile here, muy feliz, de estudiante, muy triste. So in the underground mines, They have very small space available for the vehicles, diesel-powered vehicles that sometimes go up steep grades, and they contain a lot of ore as well. So there's a lot of emission to deal with, and the ventilation in this environment is very difficult. So the photoacoustic instrument was used there to help quantify what's going on for them. This is a dynamometer test facility for diesel vehicles in UC Riverside, and it was one of our first campaigns of measurements from diesels. So there's rollers here that the vehicle is tested upon, and the roller can provide dynamic resistance. So then the exhaust from the vehicle is sent into a dilution tunnel here, constant volume sampler, and then the sample goes to instruments for measurements of chemistry and physics of particles. So this was one of the early campaigns where we realized the great utility of the photoacoustic instrument for measuring particulate emissions in source testing. So this is a campaign where we measured in Los Angeles from the fleet of vehicles on the street of Los Angeles for EPA, as many vehicles as we could test so that they could have some idea of how to do their mobile modeling for vehicles under different driving conditions. So we tested old vehicles and newer vehicles, and gasoline-powered vehicles, as well as freightliners, large trucks that transport goods as well. And this is an example of our testing. So I've got black carbon concentration on this axis and a typical test over here. And that occurred over this period of time, where we had the vehicles brought in cold, so that they were just started at this point, and then they were driven through a driving cycle that consisted of somewhat vigorous driving in here, and then sort of not so vigorous here, and then driving as if going onto the freeway here, and then less vigorous driving here. Then we let the vehicle sit for a while and repeated exactly the same thing, but with a warm start, as if you had just started a warm vehicle instead of a cold vehicle, and looked at the differential. So when we see the very clean case of this Camry, then in the cold start, the vehicle had the greatest amount of black carbon emission during that time. And when we look at the companion time after the warm start, there's essentially no black carbon that's emitted then. So once the vehicle is warm and the catalyst is working and everything is going well, then there's less black carbon emission. But if we look at the aggressive driving cycle here and here for that Camry, they're about the same. This is if you're stepping up to get on the freeway, driving very aggressively. So then let's look at the opposite extreme at this let's see, diesel, this Mercedes 300D Turbo. This was a diesel-powered vehicle as opposed to gasoline-powered vehicles. And that vehicle was pretty old and not working too well. And it produced a lot of black carbon for the entire time of the test, and no matter what we were doing with it, just an enormous amount of black carbon. We found also that we were sampling the gas emissions from this vehicle, and it had a lot of benzene as well. So we figured out Mercedes-Benz and benzene. Oh, some connection. But this was a very old vehicle, and the age of the vehicle and how well it's kept has a big influence on the emissions that come about from it as well. So this also highlights the need of very large dynamic range of measurement for tests like this. The next thing I want to talk about is the aerosol light scattering measurement. This is with the reciprocal nephelometer method, and that's what we like to use because it's very appropriate for laser light sources. The nephelometer gives a measure of the total scattering cross-section, and real nephelometers, of course, have real problems. They can be infinitely long, so they have some truncation effects. They have problems with large particles, and potentially with heating if you have very hot light sources that you're using. So this next example comes from measurements in Mexico City during Milagro in 2006. Our data today that we're going to talk about is from T0 in the north part of the Distrito Federal. And the thing that we ended up really studying a lot was whether we had primary emissions affecting the aerosol optics or secondary transformations affecting the aerosol optics. Primary emissions come from the various sources, and the secondary effects come from gas to particle conversion and particle mass being created by photochemistry and chemistry in the atmosphere. So this was our measurement of the aerosol optics on average during the Milagro campaign. We saw that the absorption coefficient reaches a peak during the morning rush hour and then diminishes as the day goes on because the boundary layer mixes, and then it starts to rise a little bit in the evening, but the peak for absorption is in the morning rush hour. The scattering, on the other hand, on average, peaks at a much later time. And so we were puzzled by that for a while, not having done measurements here before, and came to the conclusion that it's most likely the secondary aerosol that's formed during the day from photochemistry that contributes to the scattering, in addition to the primary emissions, just like in the case of the absorption. Then the extinction, being the sum of those two, is given there. So this is now a depiction of the extinction coefficient along with the single scattering albedo. And the single scattering albedo, remember, is low when there's a strong influence of black carbon and high when there's a strong influence of scattering. So this is a good measure of seeing very quickly which type of aerosol is affecting the air mass, and also get an idea of what its radiative forcing impact would be. Be very strongly absorbing in this case in this time, and strongly, maybe cooling in this case. Okay, the next thing that we did was to look at the comparison of the aerosol optics with the chemistry measurements that were done with the aerosol mass spectrometer by Jose Jimenez. And this is a bit of a complicated figure. So we have the same 24-hour time period. We have the scattering measurement shown with this axis here and this curve here. And then we have the total sum of all species, organic aerosol, black carbon obtained from photoacoustic, nitrate, sulfate, ammonium, and so forth. The sum of all of the mass from the mass spectrometer is given by the dark curve here with the square symbols. And we see that there's generally sort of a correlation between the total, what we call PM1, with the scattering measurement. There's some deviation during the middle part of the day, probably because the aerosol size is different now at this time than it is at other times, probably a little bit bigger, maybe a little bit more efficient at scattering. And the other thing that we see is that when we look at the species that represent the secondary chemistry in the atmosphere, the nitrate and the oxygenated organic aerosol, we see that they also are peaking at the same time where the scattering peak is occurring as well. So that helped us come to the conclusion that what we were seeing in this effect on scattering was coming from these sorts of species from a chemical perspective, and it was secondary aerosol formation in the atmosphere creating it. That's very important because if you are trying to regulate and deal with PM concentration in a city, and a fair amount of it is coming from secondary processes, you must also somehow deal with that in addition to the primary emissions. The black carbon aerosol associated with absorption is only coming, there's no secondary process which creates it by comparison. Okay, so when we looked at the scatter plot of the AMS mass concentration and the scattering by the photoacoustic instrument, we saw that there's a reasonable correlation and came to the conclusion that we could more or less use the scattering measurement for a PM1 measurement by dividing by this factor in appropriate units, and we would get a mass concentration measurement. So in cases where you have no PM measurement at all, but you have a scattering measurement, it's useful to do some comparisons that way. Now I want to show some preliminary work from the stuff that we've been doing in the last 2 weeks with Raphael Lignan and the group of Gemma and Oscar. So we can see some comparisons, initial comparisons between what we saw at T0 and what we saw at CCA in the January, February, March time frame of this year. So first off, we have the same kind of 24-hour averages here, and we look at the absorption coefficient. Well, it peaks a little bit below 100 here, and it peaks at about maybe 30 at CCA during this time. And if we look at the scattering coefficient, it also, as did in T0, peaks later in the day, indicating likely contribution of secondary aerosol. And the amount of scattering is about 100 here compared to about 175 here. So when we look at the single scattering albedo, the rush hour time where the aerosol is very dark is very broad in the case of T0, and in the case of the CCA it's narrower. And the deviation between evening and daylight hours between for the single scattering albedo is less pronounced at CCA, maybe indicating a difference in the quantity of secondary aerosol formation that's going on as well. So it's very interesting to have this comparison, and we have much more data to look at and much more to do, but it's looking good. Okay, now, in order to gain an insight on not the 24-hour average, but the overall campaign, we look at graphs like this. So this is the day of the year during the campaign, and this is the hour of the day. And so what we see, for example, is that around the 20th, at around 8 a.m., there was a lot of light absorption going on during the rush hour. But we see that that's not just constant every day. There's quite a variability in the structure of that absorption, and it sometimes maybe starts quite a bit later. Sometimes we have meteorological impacts where we have clean air coming in as well. So there's a fair complexity to the signals that we're seeing, to the data as well. Temporal behavior is complex. The scattering measurements also show that same sort of complexity. They show the peaks coming later in the day on average, and generally a correlation with the absorption measurements as well. So when we do the same thing with aerosol mass spectrometer data, we'll be able to gain a lot more insight because we'll have the chemistry that we can look at for the way that this breaks up. So the extinction coefficient is shown here, and the single scattering albedo as well. That's both exhibiting the same sort of complicated behavior. What time should I practice or aim at quitting? 10 minutes? Okay. So this next example is how we use the photoacoustic instrument in order to assess the validity of satellite remote sensing of PM 2.5 with, for example, the MODIS instrument on the satellite. That's an important consideration because there's a very strong effort, a strong desire to use satellite measurements for PM 2.5 in air quality applications. But it has to be reasonable in order for that to be done. And so we have, for comparison purposes, we use our photoacoustic instruments for measuring the extinction, which is what the satellite remote sensing is sensitive to. And we also use our ground-based sun photometers, like our CMAL, which of course exists in CCA as well, and we have one in Reno at UNR, and we compare with satellite remote sensing as well. Then we have the beta attenuation instrument, which is a PM 2.5 instrument that will provide sort of the ground truth of what the PM 2.5 is. This provides ground truth for what the extinction coefficient is. We have the CMAL sun photometer, which provides the true aerosol optical depth of the entire atmosphere. And we have the satellite remote sensing, which is used only after a complex algorithm is employed to retrieve the aerosol optical depth. So this is a setup that I'm thinking of here. We have the ground, we have our sun photometer looking at sunlight through the entire atmosphere, photoacoustic instrument at the surface, satellite, which is seeing both the light that's reflected from aerosol in the atmosphere, as well as light that reflects from the ground after passing through the aerosol. And that difference is what is making the satellite measurements very complex. The satellite measurement has to deal with this ground reflection in order to pull out what the aerosol might be doing to the signal and to retrieve the aerosol optical depth. So I want to define H as the height of the atmospheric boundary layer, the mixing layer in the atmosphere. And we would like to assume for satellite remote sensing or CMEL use that the aerosol exists only in the boundary layer. If it exists outside of the boundary layer, then it has no relationship with surface measurements of PM 2.5. So the way that we can evaluate that question is that we say that H is the true boundary layer height at a given time, and we define an apparent optical height of the boundary layer, AOH, as equal to the aerosol optical depth divided by the extinction coefficient measured at the surface with a photoacoustic instrument. Column property divided by in situ surface property. And this has dimensions of length as well as the boundary layer height. So if the boundary layer is being all the aerosols in the boundary layer, we would expect the apparent optical height to be equal to the boundary layer height, or at least be close to it, reasonably close to it. So because this is going to be optical, it's going to depend on wavelength as well. So our looks in Reno at this question are now depicted here, where we have the average behavior during 3 months in 2012. We have June, which was a very clean month, just coming out of winter, and fairly windy for a portion of it. July was getting dirtier, and we had some impact of biomass burning in the area. And August, where we had quite a lot of biomass burning affecting Reno. So when we look at the temporal behavior of the apparent optical height, that during the day at 870 nanometers in the near IR, the 870 being more sensitive to the coarse mode aerosol, we see that the boundary layer height, H, that I mentioned, is pretty close to the aerosol, the optical height, at the time when we have measurements that overlap at 4 p.m. in the afternoon. So for the 870 nanometer wavelength, we might conclude that you could maybe do satellite remote sensing to learn of the extinction coefficient near the surface. Therefore, if you use retrieval algorithms that use the longer wavelengths, then maybe they're reasonable for PM 2.5 from satellite. However, when we look at 405, or the shorter wavelengths, we see that the apparent optical height is much larger than the actual physical height of the boundary layer. And that's indicating to us that most likely there's aerosol, fine mode aerosol above the surface, most likely from secondary aerosol formation as well, that is affecting strongly the column optical depth, but not affecting the surface extinction. So if the algorithm uses short wavelengths for retrieval, it probably is going to be in error for circumstances like this, where it's clean. And when we look at August, where we had a lot of aerosol in the boundary layer from smoke, from fires nearby, well, in that circumstance, both the longer wavelength and shorter wavelength were in reasonable, more or less, agreement with the physical boundary layer height as well. So we can conclude that under circumstances where we have boundary layer smoke, the retrieval algorithm in principle from the satellite should work independent of the wavelength choice. So in order to assess whether or not the satellite is useful, we need to have the vertical profile of aerosol optics as well. This is an example of measurements we did with Twin Otter aircraft that was mentioned by Greg the other day. And we were flying over north central Oklahoma, and what we found at pretty high elevation were several layers of smoke that you can see that were separated from the boundary layer as well. And this smoke layer, this was Oklahoma, this smoke layer we traced back to fires in Siberia. So this would be an example where the measurements from the satellite or for the sun photometer would be in error when you're trying to prescribe what's happening at the surface, because there's a lot of aerosol well above the boundary layer too. Now, the next way that I think we can look at the vertical distribution of aerosol is that, it's possible to use the LiDAR during the course of the day, Raman LiDAR or LiDAR, and you can measure the presence of aerosol and look at the question of whether the aerosol is in the boundary layer or not. So the assessment can be done that way. And I think it would also be very good to do comparisons or look at the vertical profile of aerosol with the balloon system at UNAM as well. So I'm very excited about that prospect. I think I'll skip this one because we really are getting close to the limit. And then get to the end here, where I want to go through the sort of trends, needs, and conclusions. Generally, the filter-based measurements, 8 thermometer and PSAT, need to be processed with algorithms to reduce the aerosol scattering and filter loading effects. And that's becoming more current in the literature when we submit papers, and people don't like to see the raw data. They want to see it somewhat processed by algorithms like that. Much current work is going on the optical and chemical properties of brown carbon aerosol around the world to try to identify how common it is and what the different sources might be besides biomass burning if they are there. So that's a chemical and optical question as well. And I think we need to continue to very thoroughly evaluate satellite remote sensing of surface PM 2.5, especially with the vertical distribution of aerosol physical and chemical properties. And that's partially because this is such a convenient thing to do. There's going to be a tendency for our cities to be evaluated for the likelihood of being a livable city based on retrieval of PM 2.5 from satellite. Well, if it's in error, we could end up in being classified incorrectly. So to get the most out of the aerosol optics networks in general, it's useful, as I mentioned earlier, to use the PM 2.5 estimation from the scattering measurement if there are no other sources of PM 2.5 measurement. It's a useful tool. And I want to thank my collaborators, students, and other researchers over many years, funding agencies. And additional information is available from my website, where I have publications here, presentations including this one here. And if you want to look at the real-time air quality in Reno, you can go to this website here, which will show the black carbon and PM 2.5 concentration. And now I want to thank you for your attention as well.
Thank you very much for this stimulating talk. Any questions or comments?
Thanks a lot for your presentation. Very nice to hear about acoustic methods. I'm very curious about the plot that you have for the AODH, the aerosol optical depth height, where you show for a given day, you have one line that is a red one, then a blue one, and then you have a point that you actually measure with boundary layer height.
Yes.
And what caught my attention is that if I look at this plot, I believe that the red one is the one that I will probably trust to be a good proxy for boundary layer height.
Yes.
However, during the day, it seems to be very high in July. In July, between 8 and 12, it's a lot higher than what it is during the afternoon, when I was expecting the boundary layer height to be mature. But it seems to be it doesn't seem to be catching the early moments of the boundary layer development versus the mature part of it, although when it's fully developed. Is that correct? Or?
Yes, I would say that's true, that there would be reason for not exactly trusting the optical determination during this time as well. And during that time, the morning rush hour has already occurred. The sunlight is beginning to mix the atmosphere as well, and perhaps any kind of residual layer is going to have an impact as well. So I think that it looks good later in the day, but not always during the earlier portions of the day as well. The 870 nanometer wavelength, the red curve, is going to respond both to probably more strongly to the coarse mode aerosol and also some to the fine mode aerosol. So there's some question about what the mixture of aerosol is during this time as well. So if you have aerosol which may be at the surface but not in the column or vice versa, that's going to have the impact to give this kind of behavior. But it seems clear that the short wavelength determination is that the boundary layer height that we calculate optically is clearly above what we would measure for most circumstances. And the satellite retrieval algorithms tend to use roughly about 440 and 660 nanometers for their retrievals, and so they're going to be probably more like this than this, and so that adds question, and it's sort of an interesting question in general. We're trying to understand it from a physical perspective about what's happening. One thought is that very near the surface, perhaps because we have a pretty good mixture of coarse and fine mode, that the coarse mode may be even aggregating some of the fine mode near the surface, and so that causes this effect here to be much higher. So we don't have as much fine mode near the surface as is in the whole column of atmosphere.
According to the 2006 data you showed and the more recent data, you have a secondary aerosol which is clearly dominant. So the primary soot or primary black carbon, I think of it as the black smoke coming out of the trucks now. So this is basically not the main problem. What would be the most efficient way how to reduce secondary aerosol formation or secondary aerosols in the atmosphere?
So that is a pretty deep question, and I think that one is going to involve a bit of understanding, a lot of an effort to understand exactly what gas phase transformations are giving rise to, especially the secondary organic aerosol. There's some secondary nitrate, but it's really a secondary organic aerosol issue. So then I think the need there is to strongly couple modeling efforts that can put in chemistry, both the primary and secondary sort of interactions, and put in as many measurements as we have available for species of gas phase aerosol, and look at the reaction rates for the different types of gas phase constituents to see which of those tend to be the largest contributors. And then at that point, then if possible, then you can try to address from a societal perspective those gases that are going to contribute most strongly. But it may be, and probably is, circumstance where it's a complex chemical reaction involving lots of different components, different gases. So it's, but it really helps, I think, frame the problem, because having such a secondary effect, it points out that you can't just look at the primary emissions for trying to deal with the overall air quality problem. So, but yeah, good question.
Thank you for your presentation. Now I'm going to ask a very naive question. Okay. I'm going to use an analogy first. There's a methane and alpha-pinene. Methane has a very simple IR spectra. Alpha-pinene has a very complex IR spectra. Mole by mole on their own. Alpha-pinene is very much a stronger greenhouse gas than methane. But we don't bother about alpha-pinene because residence times is too short that it doesn't matter. And black carbon has the portion produced by black carbon longs only 2-3 hours before it starts to drop because of the aerosols start to change and to hydrate and to get secondary organic aerosols. So the question is, using that analogy, is why to bother about black carbon?
Okay. Well, besides being very entertaining, so when black carbon during the daylight hours is created during that rush hour, it peaks because the boundary layer is not well mixed at that point. And so then the concentrations, especially at that time, are really localized to where you're at. During the day, the black carbon, it hasn't gone away. It hasn't gone to the surface. It hasn't deposited. It continues a life elsewhere. So it's going to be most likely carried into the atmosphere where it'll go downstream through wind, and it will be diluted in concentration downstream so that it's no longer like it was during that rush hour, but it's going to continue to affect radiation transfer in the atmosphere as well, downstream of that initial generation. So it'll eventually, it tends to be pretty hydrophobic when it's first created, and so it's not going to immediately wash out with rain. After some processing in the atmosphere by oxidants, it may become more hygroscopic and can fall out, but roughly the lifetime might be on the order of about a month for the black carbon. So then in that circumstance, it's going to be affecting the atmosphere for an appreciable amount of time before it goes away. So it's not just that initial push where it's important, but we think of it for having about a month impact. And the thing in the atmosphere is that we keep putting more black carbon in every day. So the concentration is going to remain. And I guess the good thing about that is if we decided to quit putting black carbon in the atmosphere, then it would disappear from the climate scene relatively quickly. It would be gone. And of course I'd be out of business. And that.
Okay, but now another question. Do this aerosol goes through a cycles going is black, brown, and later on can be black again and then brown again?
So with the processing that we saw in the atmosphere, maybe from the collapsing of the black carbon aerosol, when it starts off fresh, it's this large particle that's very open, very susceptible to absorption. Each monomer can absorb light. And after it has collapsed into that more compact shape, now the monomers on the inside no longer are available for some wavelengths to be absorbed, and so as a consequence, then the absorbing or the heating effect is less important there. So then it becomes a question of exactly what is happening to the air mass once it departs from the origin of creation, and when humidity can cause that sort of collapse and change of optical property, but in addition, the organic aerosol some of the organic aerosol can cause the same sort of impact. And I think the changes occur sometimes when we look at biomass burning, smoke plumes in Reno. We had lots of smoke in summer. We see the change of the color and the smoke starts off quite dark and then fairly rapidly turns to a lighter color downstream. There's processing of some sort that's going on. And you still have some absorption going on, but now you've increased the amount of scattering at the same time because the particle in a more compact shape will be a stronger scatterer. And if it also has some aggregation of scattering material on it, it will also be a stronger scatterer. And it's that single scattering albedo that's important for figuring out the climate effects. So it hasn't gone away during processing, but it's probably diminished the impact. So the fresh emissions are going to affect our cities mostly. They'll affect the radiation transfer in the city, the mixing and the dynamics of the atmosphere in the city, especially in those morning hours when the boundary layer is beginning to expand. And but downwind, there certainly will be different optical properties for the aerosol than they near the surface.
Patrick, continuing the question of Michelle, where you show that secondary organic compounds are very important, especially during the afternoon. This was during the Milagro campaign?
Yes.
Well, during the Milagro campaign, there have been changes in the diesel used in Mexico. When you were here, the diesel was with at least 100 parts per million of sulfur. Mm-hmm. And now we're supposed to have low sulfur gasolines and diesel. Mm-hmm. Do you think that if you make the same measurements today, you think there could be a change? That because of the change in sulfur content of the gasoline and diesel?
Let's see. So it could be that maybe with the change in the sulfur content, that it might change the size of the black carbon particles.
The formation of secondary organic compounds.
So the secondary formation, if it's a sulfur, the sulfate wasn't a strong player in the Milagro campaign. It was really the nitrate, and especially the organic aerosol, the secondary organic aerosol. And so from that, just from a sulfate perspective, it may be that there wouldn't be so much of an impact on the secondary aerosol. But looking at the overall broad perspective of the emissions, that if the sulfate is used and the size of the aerosol that comes out is smaller, then the character of the combustion itself may be different. And so if it goes to more complete combustion, then it may have less of the precursors. But it's the really important question that we have to look at is what is the primary sort of precursor for secondary that is at play here. So if we had complete combustion in all the vehicles, then at least we could rule them out. We still have cooking, we still have sort of maybe fugitive emissions of various kinds of gases too. That would have to be looked at. But that's an interesting question. It'd be very interesting to repeat at least some of the measurements at that same location now, maybe with the mass spectrometer and the photoacoustic instrument at the T0 site at EMP, to see exactly, during the March timeframe, to get another snapshot to see how things have changed. That would be, you always have to worry about how the meteorology is during those times, so that, if you happen to have a month that's very dry and very stagnant, you would have quite a different value than if it was rainy the whole time or something. But it would certainly, that would be a very good thing to do, I think.
Thank you, Pat, for your talk. I like it. Let me make the comment in Spanish, because I know that you will understand Spanish.
Más o menos.
Please go to the results of the campaign in 2015. No. Okay, it's okay. No. Another? Yes, okay. La diferencia, creo yo, que está entre el lugar, influye mucho que las mediciones de arriba son en el IMP, en T0. Y acá las mediciones son en el Centro de Ciencias de la Atmósfera, en el sur. Lo que vemos ahí es el carbón negro, black carbon, el coeficiente de absorción, ¿sí? En ambas están como, el pico está como alrededor de las 8 en Ciudad Universitaria y alrededor de las 7 en el norte de la ciudad. Yo creo que ahí tiene que ver el tipo de circulación que hay de los automóviles y de los camiones, etcétera, ¿no? Y creo yo que podemos después conseguir los datos que hay en la rama en Vallejo. El lugar de Vallejo queda en línea recta al IMP como a unos 500 metros. ¿Sorry?
The last part.
¿Ya? Y podemos conseguir esos datos.
Okay.
Sí, podemos conseguir esos datos. Y la pregunta que hacía Aarón, yo creo que la podemos responder con esos datos, porque tenemos en el mismo tiempo, tenemos mediciones. You understand?
So I think so. So you have measurements that are going on at a close location?
Yes, Vallejo. Okay, the same instrument. The Rama has the same instrument that we take in this.
Have here.
Okay.
Yeah. Okay. So that will be useful. I think very useful for looking at. It's close enough. And then in 2006, the Rama site also was active.
Yeah.
During Milagro también.
Okay.
Sí.
Okay. Thank you.
Sí.
Más preguntas. Just to comment. I think you are using BRC to denote brown carbon. Will the UPAC be buffer because it could be confused with bromine carbide?
Oh, yeah.
So I would recommend to change the.
It's becoming common, so it's probably good to make that change soon before it pervades the literature. Also, I guess the brown carbon could be really, some part of it could be dust as well. The other thing that we found in doing a detailed look at brown carbon was that sometimes when you have organic carbon coating black carbon, it can cause enhancement of absorption, and it looks like brown, but it's just an enhancement of absorption, nothing to do with brown at all. And so there's probably some better way to describe it, but yeah, you're right. It looks like bromine carbon.
Just like AMS and its accelerator mass spectrometry, and many people use also mass spectrometry. Very different things. Okay.
It makes sense to compare, for example, March and February. The daily cycle is the same in these 2 months, or maybe could be a variability from month to month?
Yes, I think that there is a transformation that begins from month to month as well as the seasons change, for sure. But the boundary layer behavior during the day is going to be different as well. So it's as close as we can get for a comparison, but not exactly fair in that regard either. So that would impact things too. So it's interesting too to wonder about the behavior, the needs of the society near the T0 site compared to what happens, if there's a lot of buses that are waking up to transport in and out of the northern part, that might be different between the 2 locations as well for the timing. That was kind of our thinking of why the timing was so early. It seems a bit early for this at the T0 site, is that it might be the buses and the location there that were getting busy.
Thank you very much. Los invitamos a pasar al vestíbulo. Los invitamos también a la conferencia de mañana.
Con marzo para comparar febrero de Seúl con febrero de Vallejo.
Los datos también, sí.
Let's see. So
what wavelength is the cavity ring down? What wavelength? Yeah, okay, so probably 532. Was that the LED based? Or the LED based cavity ring down instrument?
No, because when you use PCFP to take some information about the absorption patterns, they use most other work from Texas that they're using
Okay, yeah, so Texas A&M.
Yeah.
Okay, so then the cavity ring down, we built those instruments before and used them as well. And so then it would be good for the extinction coefficient in that case, and should be pretty easily, should be pretty accurate. So then for comparing with the CMA, it should be very good in that case. So you can't tell, of course, did they have a scattering measurement with it also, or just the cavity ring down extinction?
Yeah, in this case, we have data for extinction for
So was this Renyi Zhang, the group of Renyi Zhang?
Exactly the same.
Yeah. So that's probably good for comparison with the CMA. And we found that the cavity ring down is it's a bit tricky to do, but it's quite accurate and quite sensitive. The key thing is we have mirrors, you have two mirrors, and you have a light monitoring the light. Yeah. If these mirrors get dirty, the light does not go back on. So you have to work really hard to keep the mirrors clean, and that means you have to bring in some dilution air near the mirror in order to keep it from getting dirty. And so that changes the effective path of the cell too. So it makes it, you have to interpret it very carefully to make sure you get that ring, because the ring down occurs over some.
The other question is, if you have the ACC into the chamber in the cavity region, is not affected?
They will affect it. So if you have NO2 with cavity ring down, if you have nitrogen dioxide especially, it will have strong light absorption, and so it will affect it.
But the absolute coefficient of these gases is high?
During this campaign, we had, I'll show you, during the lab we were able to measure the absorption caused by gas outside, because when the instrument zeros, we get a measure of the gas effect. And so then during the gas time, we can get an idea of how much the absorption for T0 was caused by NO2, or how much, we got rid of it, but this signal is the particle part, and this is the gas part. And the gas part is pretty low, and so it didn't impact things so much. But if the other thing you can do is to use a denuder in order to take out the NO2. That's something that we've done in campaigns as well. So maybe Renyi Zhang, because he's a chemist, he might have used the denuder. So we used activated MnO2 in order to take out NO2. And it works pretty effectively. It has a little bit of particle loss, but it really deals with the problem of NO2 very thoroughly. But you're right, otherwise it becomes an interferent. If you have NO2 measurements that are at the same site, then you can look to see what the concentration of NO2 is and see that it's very concentration, how it might affect things, on how it.
You are currently the only participant in the conference.